Now, if this object over here is to be projected upwards with a velocity, say v0, it gains kinetic energy as a result, and it is able to make a height of, say, h0 and falls back to Earth after the energy gained at the point of projection is exhausted. Now, if this same object is projected upwards again with a velocity, say, v1, and here v1 is greater than v0, it gains kinetic energy and makes a height, say, h1, and after a time t, it returns back to Earth. Now here, the understanding is that when objects are projected upwards from the Earth's surface, and if we are to assume that they have no other means of acceleration other than the energy gained at the point of projection, and that they are solely under the Earth's gravitational pull, in other words, the object is within the Earth's gravitational field, they eventually return to Earth when the energy gained at the point of projection is exhausted. So under the force of gravity, they return to the Earth's surface. Now, if we are to have this same object projected at a velocity that is so fast, say with a velocity v, that it no longer returns to Earth, that the velocity is so fast that it keeps going away and never to return to the surface of the Earth. At what velocity v can this be achieved? In other words, what does it take to escape the gravity of the Earth? Now here, let's make a few assumptions here. Let's assume that A is the point of projection and B is the point where the object just escapes the gravitational pull of the Earth, and that at the point B, the object is free from the gravitational pull of the Earth, and at this point, the object no longer will return to the surface of the Earth. Let's also assume that this is the center of the Earth and the radius of the Earth is given by r subscript e. So to answer the question, at what velocity then can the object be projected in such a way so fast that the object no longer returns to Earth? So here we're going to answer the question of what velocity can that be achieved that the object no longer returns to Earth from the point of view of the conservation of energy, which says that the energy of this object at the point of projection will be the same energy of this object at the point B. So the energy of the object at the point A should equal the energy of the object at the point B. And that is the law of conservation of energy, that the total mechanical energy of this object at the point A should equal the total mechanical energy of this object at the point B. The object will have no energy losses according to the law of conservation of energy. Now, at the point A, the kinetic energy of the object is given by this, where m is the mass of the object, and the gravitational potential energy of the object at the point A is given by this, where me is the mass of the Earth, and g is the universal gravitational constant. M is the mass of this object over here. So at the point A, the object is going to have the kinetic energy expressed as such, and the gravitational potential energy at the point A expressed as here. Now, if we are to assume that the total kinetic energy of the object at the point A is completely exhausted as at the point B, where at the point B, the object just escapes the gravitational pull towards the Earth. In other words, the kinetic energy at the point B is completely exhausted, and there are no extra energy that the object possesses for further propulsion. And here at the point B, the object has theoretically reached infinity, and its velocity at this point is 0. In other words, the velocity at infinity of the object at the point B is 0. So the kinetic energy of the object at the point B is given by and the gravitational potential energy at this point is given by where infinity now is the distance between the object and the earth. At the point of projection, the distance between the object and the earth was represented by the radius of the earth. Why? Because the entire mass of the earth was considered to be concentrated at the center. Then the distance between the earth and the object is the radius of the earth. So at the point where the object is considered to have just escaped the gravitational pull of the earth, theoretically reached infinity, that is going to represent the distance between the object and the earth. So we can now put these pieces together to represent the law of conservation of energy, that the energy of the object at the point A is given by, we put these components of the mechanical energy together. And at the point B, where the object theoretically has reached infinity, will be represented by now this term of the expression mathematically goes off, and the velocity of the object at infinity, just as it escapes the gravitational pull of the earth, when the entire kinetic energy of the object is completely used, would mean that the object would have no velocity. And so this term also goes off. So v squared is equal to and finally, we're going to have V as this is the velocity by which the object should be projected in order for it to just escape the gravitational pull of the earth and be free from the earth's gravitational field, where J is the universal gravitational constant, R subscript E is the radius of the earth. Now, this velocity is what is known as the escape velocity. And it is the minimum velocity at which a body has to be projected from the Earth's surface so that it goes out of the Earth's gravitational pull completely. Now, let's familiarize ourselves with this formula, where small g is the acceleration due to gravity, J over here is the universal gravitational constant, M subscript E is the mass of the Earth, and R subscript E is the radius of the Earth. Now, let's manipulate this expression in order to make use of this expression over here. So we're going to make use of So we're going to have something like this. And if we are to replace this expression over here by J, we're going to have something of this form. Now, acceleration due to gravity is given by 9.8 meters per second squared. Universal gravitational constant is given by 6.674 times 10 raised to the power negative 11. And the radius of the Earth is given by 6,400 kilometers. Now, let's replace these values in this equation. Now, the radius of the Earth is in kilometers, and the acceleration due to gravity is in meters per second squared. And so let's convert this to kilometers per second squared, and we are going to have So the escape velocity of the Earth is approximately 11.2 kilometers per second. So it means that when a body is projected with this escape velocity, it gains enough kinetic energy to overcome the gravitational pull of the Earth and to move far away from the Earth and theoretically reaching infinity. If objects are projected with velocities less than this, the energies they gain will not be enough to overcome the Earth's gravitational pull and is going to return back to Earth. If the velocity of projection is greater than this escape velocity, then the body, after escaping the Earth's gravitational pull, will have still enough excess energy that can be used for further propulsion beyond infinity. So this is an explanation of the derivation of the escape velocity of the surface of the Earth. And different celestial bodies would have different escape velocities. Now, in our various classes, we may be confronted with various questions that are related to escape velocity. Let's try our hands on a few of them. And now we have an escape velocity of a particle of the Earth, radius r and mass m as 11.2 kilometers per second. What is the escape velocity on another planet with radius r over 2 and mass m over 4? Now, let's recall the following, that the escape velocity is given by where V subscript E is the escape velocity of a particle on Earth, M subscript E is the mass of Earth, R subscript E is the radius of Earth, and J is the universal gravitational constant. So the escape velocity of the same particle on another planet will be given by where V subscript P is the escape velocity on the other planet, will be given by where M subscript P is the mass of the other planet and R subscript P is the radius of the other planet. But we are told from the question that M subscript P is equal to over 4 and R subscript P is equal to over 2. So let's substitute this into this equation and we are going to have simplifying further, we are going to get simplifying further, we get this. This is the escape velocity of the particle on the Earth, and this is equal to 11.2 kilometers per second. So from here, we can say that it's equal to 11.2, which means that I can rewrite it as this. Which means can be rewritten as so we're going to substitute this expression over here as Vp. So the escape velocity of the particle on another planet can be simplified into this expression. which is root 2 is 1.4142. So the escape velocity of the particle on another planet is given by approximately 7.91 kilometers per second. So whilst the escape velocity of the particle on Earth is 11.2 kilometers per second, that of the same particle on another planet is 7.91 kilometers per second. So that is the answer. Now let's try this too. The escape speed of a body on the Earth is 11.2 kilometers per second, and the body is projected with thrice of the speed. Now, what is the speed of the body when it escapes the gravitational pull of the Earth? Let's try to sketch this. Now, let's consider this as our Earth, and this is the radius of the Earth. We have an object here, and that object is projected into space. Now, this body is projected from the Earth at the point A with a velocity v0, which according to the question is 3 times the escape velocity on Earth. And this gives the body enough kinetic energy to go beyond the gravitational pull of the Earth and reaches a point B. But the body is projected with enough energy. So even at the point B, it still possesses excess kinetic energy to engage in further propulsion. So at point B, it's still going to have some velocity, which I'm calling V infinity. So what this means is that at point A, at the point of projection, the body is going to have an initial kinetic energy of half mv squared and an initial gravitational potential energy of minus g me, where re is the radius of the Earth, m subscript e is the mass of the Earth, and m is the mass of the body. And at point B, the body is going to have the kinetic energy of half and gravitational potential energy of negative g. So what this means is that at point A, at the point of projection, the distance between the object and the Earth is considered to be the radius of the Earth, and at point B, which is a faraway distance from the Earth, the distance between the object and the Earth is considered theoretically to be infinity. So we're going to look at this question from the point of view of the principle of the conservation of energy, which states that energy can neither be created nor destroyed, only it can be converted from one form to the other. In other words, the total energy remains a constant, and it is said to be conserved over time. The total mechanical energy of the body at the point A equals the total mechanical energy of the body at the point B. And here we're considering the principle of conservation of energy. And so putting the formulas in place, it will mean that at the point A, we're going to have this equation, and at the point B, we're going to have this equation here, where V infinity happens to be the velocity of the body at the point where it just escapes from the gravitational pull of the Earth, and the gravitational potential energy of the body at point B is given by. Now this term will go off, and here the question says we are supposed to find the speed of the body when it escapes from the gravitational pull of the Earth, and this is the speed that we are supposed to look for. The V infinity, the velocity of the body at the point where it theoretically reaches infinity. Now, let us recall this formula. The escape velocity of the Earth is given by this. So it means that we can rewrite this as this. So we can substitute this expression over here into this equation here, and we're going to have so we can go ahead and simplify this expression over here. We're going to have let's reorganize this expression over here. Now, the question makes us to understand that V0 is equal to thrice the escape velocity on Earth. So we would go ahead and replace V0 with this expression over here, and we're going to have so let's simplify ahead. So the velocity is given by, so simplifying further, we're going to have, now we are told in the question that the escape velocity of the body on the Earth is 12.2 kilometers per second. So we're going to replace it. But we are told in the question that the escape velocity of the Earth is given by kilometers per second. So we're going to replace that over here, and we are going to have, when we simplify this expression over here, we are going to have 2.8 to 84 times 11.2 kilometers per second. And so the velocity of the body as at the time that it just escapes from the gravitational pull of the Earth is given by 31.68 kilometers per second. So this is the speed of the body when it just escapes from the gravitational pull of the Earth. And by this velocity, it gives the body some extra kinetic energy to engage in further propulsion at infinity and beyond. So this is the answer to the question. Now let's look at this question, which says that the Earth has a mass 9 times and radius twice that of a certain planet. Now we're supposed to determine the minimum velocity required by the rocket to pull out of the gravitational force of that planet. And by that statement, we're supposed to calculate the escape velocity of that planet. Now we've been given the escape velocity on the surface of the Earth as 11.2 kilometers per second. Now we are told that the mass of the Earth is 9 times the mass of that unknown planet. Now let's consider mx as the mass of the planet and m subscript e as the mass of Earth. Now r subscript x as the radius of planet, and r subscript e as the radius of Earth. So we are told again that the radius of the Earth is twice the radius of that planet. Now, let's recall that the escape velocity of that planet is given by the formula. So we can go ahead and do the simplification by substitution. So the escape velocity of that planet will be given by now reorganizing this expression, we are going to have simplifying further. Now, what does this expression represent? This expression represents the escape velocity of a body on the Earth's surface. And in the question, the escape velocity on the Earth's surface has been given as 11.2 kilometers per second. So we're going to go ahead and do the substitution in the solution. So this is equal to 11.2 kilometers per second. So we are going to get which translates into times 11.2 kilometers per second. So we're going to get the escape velocity on that planet as approximately equal to 5.27 kilometers per second. So this is the velocity by which the rocket is required to be projected to escape the gravitational force of that celestial body. That unknown body. So that planet has an escape velocity of 5.27 kilometers per second. So this is the answer. And this is the end of my video. Thank you very much for watching, but keep watching.